Florid will talk about the CNN basics. So yeah, maybe she can start now. Hi, Florid.
Hello, can you hear me?
Yeah, I can. So when you want to like flip the slide, you just need to tell me.
Okay. Okay, hello everyone. Welcome to today's lab session. This is lab 5 about CNN basics and backpropagation. And this is what we're going to do in this lab. So we're gonna first go through the CNN components, then implement, train, and evaluate the basics of CNN using PyTorch. And then we will walk through different checkpoints and then focus on the PyTorch operation. And then we take some questions about the implementation at the end. And also you have to respond to the peers polls. And you have to know that this lab was designed to help you with different assignments. You can move to the next. Yeah, okay. For today's lab, we will start the lab notebook, the codes. We'll start with the first checkpoints is about data loading. The second one is data preprocessing. The next one is exploration of data analysis. And then continue with checkpoint number 4, which is about building the CCNN model. And then checkpoint number 5 is about loss and optimizer. And checkpoint number 6 is about train the model. And then we continue with the evaluation of the model. And then we visualize the intermediate feature maps. And then the checkpoint 9 is about visualizing convolutional filters. And then the last one is about conclusion and exploration. Okay, to start with the data set that we'll be using for this lab is CFR 10. It has 10 classes, of which these classes involve different object airplane, automobile, birds, cats, different object there, just 10 classes of item in that data set. So the image size is 3 by 32, 32. So that means they all have the same size, the same height and width, and they're colored images. And there is 60K total images in this data set. And this data set is balanced distribution, which means that there is no imbalance. All the distribution, those 10 classes, the data are all balanced. They have the same equal data. Okay, to visualize how the data set is being loaded in the codes view. So there is part of loading the data path, and whereby it calls the load directory for data set, so that it checks if it exists, or if it's not there, it will download the data set automatically using PyTorch, and then it has the train, and this one, the train, to set it to true, is that it will be able to download the training set. Otherwise, it just create the test set, and then it has transform that's transform the given data in the data set using like different ways of transforming this data, like random clubs and all of that. And then it has a target transform argument that's a function that takes the target data and transform it. And then it has option of downloading. This one is set to true if the data set is not, if you want to download the data set from the internet, is set to true. Otherwise, you can set it to false if you already have the data set. For more information, you can refer to that link. Yes, to understand more about the convolutional neural network, which is the main topic that we are discussing on this lab 5. we start with a given image, and it is divided into three parts. There is a feature extraction, classification, and the probability distribution. So in the feature extraction part, we have a sliding window that is applied on a given input image. And this one, it's also left to kernel or filter. It just filter out in the image and extract different features from the image. And then these features are then convoluted and we apply the Lulu. This is for applying the non-linearity on the extracted features. And then we keep pulling by reducing unnecessary features that we don't really need, and then pass down to the next layer. And then we continue until we have the list of different feature maps that we need. For the features here, when you apply this filter on the image, it can be able to extract some features like curves, edges. Those features can be extracted again for more information, and we extract like more meaningful features like cycles or like to be able to understand like the exact patterns in the image. So those features are combined all together to the flattened layer and passed down to the flattened layer. This is one layer to be able to continue to the fully connected layer, whereby all these features are flattened, and we apply the fully connected layer, whereby each neuron is connected to another neuron. And from here, that's where the actual training is happen, and the model is trying to understand the extracted patterns, and out of it, make some decision. And for the final output, we use softmax activation function to apply some probabilities for some extracted or for the predicted image to predict if it's a horse, zebra, or a dog. And the highest probability was the image is zebra. And for some points, if the model make a mistake, it can still go back, and we update the weights for the gradient adjustment.
Um, yeah. Oh, yeah. Maybe I can start from here. So, now we're going to see some detailed implementations in PyTorch you are using the labs. So, actually, you don't have to implement your own like your homework P1s when you do the labs. You just need to use the functions in the PyTorch. So firstly, it is the um, convolution 2D part, and you can directly call convolution 2D by input your in channels, out channels, kernel size, stride padding, and I actually think the rest of the parameters you may not just set them to default and initialize them. Oh, and here is how convolution works. So you can like input your channel, your input size, your strides, and you can calculate your output size by the formula in the downside. And when you see the animation on the top, you can see how the like kernel works when it gets through the matrix. And we also need pooling operations because the original matrix may be too large and we want to extract the features of it. So max pooling is just find the max value of the kernel, and it goes through the matrix, and average pooling is just gets the average value among the elements. Yeah, and here is the implementation of max pooling in PyTorch. So I think it's the same. You just need to set your kernel size, stride, and padding, and the other parameters you just need to set it as default. And when you train your model, you have to set your criterion. So I think in homework 1, P2, you've already found some place to set your criterion. So you can set it as cross entropy loss, which is the most used one. And also, you will have to use your optimizer when you train your model. So one typical optimizer is Adam optimizer. And also, I believe the main parameters you will use is only the learning rates one. It is by default set to 0.001, and you can also set your like least learning rate and your weight decay to avoid overfitting. So also in CNN training, you will also use SGD for your training. Um, the Actually, in your like homework 2P2 or in his lab, when you use SGD for training, we suggest your learning rate to be set as 0.01, not 0.001. And we also have talked about these optimizers in class before, so we just need to use them for training. And next, we are going to talk about some common training loop. So the training loop mainly requires 5 parts of things. The first part is model. You have to define your network, whether it's just like linear networks or it's like CNN networks or transformers. You have to initialize a model for it. And the second part is data. You have to load your data from your storage and get into your data loader for training. And the third part is loss or criterion. We have talked about it before, like the cross entropy loss. And for the optimizer, you can also choose whether like Adam, Adam W, SGD, and other optimizers. And for scheduler, you can mainly use like a sign scheduler or reduce on plateau scheduler, but it is not that necessary. But um, we believe you have used that in your homework 1 P2s. It is used for adjusting your learning rates. So as shown in the slides, you have to first initialize your model and get your model into the train mode, which means your dropout will not be counted in your train mode, but your dropout will be applied to your train mode. But if you are going to evaluating it, your dropout is not counted. And we also can initialize the loss. And in your forward path, you have to first zero your gradient. So if you don't zero your gradient will accumulate across your steps. For example, for this batch, I have a gradient, and at the next batch, my gradient will be accumulated to the past one. So it's like adding your batch size. And by default, you will just zero grad your gradient each iteration, but maybe when your GPU RAM is not big enough, you can try to zero your gradient. For example, for 2 steps or 3 steps at a time, it can act as adding your batch size when training for stable training. And next is we have to backward your loss. To backward your loss means you have to um, calculate the gradient, and optimizer dot step means it backwards your it backwards your gradient and updates the parameters. So here is a really simple training loop. So we have to iterate the data loader and first zero the gradient, and next get the training result of the model and initialize the loss, and um, backwards the loss and update your training parameters. Yeah, and I
I
think,
can,
yeah,
I can take over.
yeah, go ahead.
Okay, yeah, this is one of the CNN model, Alex Knight. It was developed a longer time ago in 2012. And this is how it actually worked. Start with a big image, and then the size 227 close 227, and we apply the sliding window over it, the filter over it, the Kernel filter with the size of 11 by 11, and after extracting some features from it, we move to the next layer, whereby we reduce some, we extract important features from it and pass down to the different layers. So this one, it has multiple convolution layers, whereby we keep extracting only important features from it that can be used in final fully connected network for classification, for image classification purpose. And after convolving over this image, we get the final layer, which is flattened into one long 1D dimension, and then this one is passed into fully connected network layer, whereby at the end of the prediction, they were able to predict different 1,000 classes using softmax activation function. Yeah, this is another example of CNN model that was also developed right after that Alex Knight. And this one was, main purpose for this was to solve the issues of vanishing gradients, because for the deeper modules, for the deeper layers, the deeper you go, some gradient might vanish, because depending on how model goes deeper and you want to do the back propagation, as you go back and you go deeper, some values may diminish and you end up with finishing gradients. So this one was developed to solve that issue by creating different residual networks, whereby instead of going deeper into different layers, you just combine those layers into different residual network, so that if you convolve from one layer to another, you have the possibility to apply the shortcuts from the input delay to the output. And these residual networks were created for solving those issues of vanishing gradient, and ensure to skip different connections, and also to progressively downsample with increasing as we increase through different channels. So it's the same approach, is that they implemented this way of skipping some connections so that we don't run into this issue of vanishing gradients. So the next one is mobile net version 3. This one was developed for these light-weighted resources like mobile application, whereby this one is start with a bigger image and pass down to the pass down to different layers, different convolution layers. And the best part of this model is that you start bigger, and at the end you squeeze them into smaller layers so that it can be able to fit into those lightweight models. And it was simply designed to be efficient with a depth wise, and also considering those lightweight mobile application or other devices that don't really have to support the bigger models. So they also use the bottleneck. Okay, yeah, you can proceed to the next slide. Yeah, so apart from those ones, there are different models that are under CNN, and those ConvNext, DenseNext. All of these, they are applied in image classification, and there are some examples of the different models that you can refer to when you're building some task related to image classification.
Yeah, so now we can talk about the feature maps. And each feature map represents one feature responses. And when you see the like bright part, it's like the activation is very large. And the deeper layers capture more abstract features. So you can see here it is like the first layer, and when you go through, it is go more and more abstract, I think. And filters and weights define the model's ability to extract relevant features. So we visualize them here, and visualizing them can help us understand what kind of patterns the model prioritize. So it is more about making your black box deep learning into some theory we can explain, such as edges or texture in image data, offering an intuitive grasp of the network's internal mechanisms. And here is also an example of the features. So, yeah, is there any questions? If there is no questions, we can head to the coding part. Yeah, so let's just go coding. And the notebook have been shared on Piazza, so we can open the notebook. And first, so first, I think we can just run through the first part and finish the checkpoint one. So here is just a very simple example of 2D convolution and feature method extracts. So you can just run through your first two blocks and head into your first checkpoint. So in the first checkpoint, you have to use your PyTorch to load the C410 dataset. Yeah, actually, I think you can finish both 1 and 2 because they are like all data loading process. So when you finish your checkpoint 1 and 2, you can also vote on Piazza so we can know where you are. In checkpoint 1, it is just using the PyTorch API to download your C410 data. And in part 2, you just need to implement the transform function. So let's just move on to checkpoint 3. I think you do not have to implement anything here. You just need to run the cell to get a sense of the data in C410. So here is the training samples of images and labels in C410. And after you visualize the training set samples, you can move on to checkpoint 4 to initialize your CM model.
Uh, Hello.
Yeah, hi.
Yes. Can you double check the settings of the notebook? Because they're saying they're not able to download or edit the notebook.
Oh, so they cannot copy it, or so so
They're
the
not
prob
able to open in the Colab either or download it in Colab.
yeah, I think when you use a notebook, you can just make a copy and run on your own because we want to keep the original one to be not edited. But yeah, I think I will like upload a new for you to download. Just a moment. I also provide a Google Drive link on the Piazza, so maybe you can also refer to that link.
Sorry, I didn't get you well.
Um, yeah, I mean, so you can also click this link for downloading the notebook if you have no access to copy it or run it. You just need to use this one to download your notebook. Yeah, and in check 4, you just need to like also like in your homework 1P2, you can just initialize your model. And let's move on to checkpoint 5. You need to initialize your optimizer and your loss. So we use cross entropy loss here, and we use Atom for the optimizer. And yeah, let's move on to the 6 checkpoint. You need to train the model, and the main thing you have to implement is just like the simple training sample we show in the slides. You have to first zero your gradient and then get your output of your model and backward to your loss and optimizers step, and I think that's all. So you need to implement your basic training loop here. So after you implement it, you can start training with it. And I think maybe because I use CPU, it could be really slow, but you can train it for several epochs. Yeah, let's just move on. So you can wait for your model to train it, and you can also implement your evaluation code with your model. So evaluation is like the training part. You just um, need to find your data and loss in your test sets. So after training your model, you can run your evaluation part. I'm gonna make the type back. So for the time, I just set the epochs to 1. Yeah, and we can evaluate the model. So the test accuracy is actually not that good because we only train it for 1 epoch, but if you train like 10 epochs, it could be very good. It's and now let's visualize the future maps. So you don't have to modify any code here. You just need to run the cell. So here you can see the visualized feature map in your model. And we can also visualize the convolutional filters. But actually, this is the kernels you use for your model. And then that's all for the notebook. So you can either wait for your training or just go through the code to debug or find if there is any mistakes in your code. Yeah, and I think that's all for today. If you have finished your notebook, is there any questions? If there is no, I think that's all. So, Flory, do you have anything to comment or?
Okay, there's someone who asked about the checkpoint number 4. How do you determine in input channel, output channel, and input channel are for 3 RGB channel and output channel is number of features. Yeah, it's about the network, the class network.
Yeah, could you say that again?
Okay, yeah, that's the part for the checkpoint number 4. For the 3 RGB, the 3 RGB is just for showing like those images are colored images, or they're not like gray images. And for the input channel and the output channel, it depends on the type of the network you want to build and how you want to be converting throughout the images. And yeah, it depends on how you want your network to be like. And for the input channel, if you like, you give it 3 RGB just to show that it's for red, green, and blue, just for colored images. And then for the output channel, is set to 32. This is the number of features. I don't think if I got it correct.
Yeah. I think, Flory, you're correct. And the in channel is actually the RGB channel, and out channel is the channel you want the model to. Like, for example, I want to add parameters in my network, and I want to learn more information in the network, and I can add the channel. But the in channel is 3 because it is just RGB.
Okay, so there's a question not related to lab, is about the Slack deadline. Yeah, there is a Slack link for joining for those who want to submit late. There is a link for the Slack deadline. Mhm.
Yeah, so is there any other questions?
Okay, Grace. Okay, Grace, did you use the Slack for the Slack link to join the competition? Because I think okay, you want to submit the final code. For the final code, you use the same AutoLab link. It will be marked as you'll be using your late submission days. So if you join the Slack competition, you will still get your full marks. For the submission, you can use the normal Slack, normal AutoLab for the submission. Let me send you the Piazza post that explain everything about the Slack days.
Yeah, so if there is no other questions here, I think we can stop here.